Welcome to the computer vision webinar. The webinar will take roughly 1 hour. I will show you a C# application to do a face swap operation. So I'm going to take one picture with a lot of faces, and I'm going to put my own face on top of one of the other faces. And I'll show you how to do that whole thing in C#. So it will take roughly, I think, 45 minutes to go through the entire demo. And then afterwards, there is time to take some questions. So I'm hosting this webinar together with Sonsoles. Sonsoles has graciously offered to co-host with me to collect your questions during the webinar. Sonsoles, to you.
Hello everyone, this is your co-host Sonsoles, and I have a couple of announcements to make regarding how the chat works. If you go to the chat, you will get a drop-down with a number of options. If you want to let everyone know that you are here, please choose everyone from the drop-down and post your message. And if you have questions for Mark about today's topic, please choose co-host Sonsoles from the drop-down. Let me repeat that. If you have questions for Mark about today's topic, please choose co-host Sonsoles from the drop-down. 10 minutes before the end of the webinar, Mark will answer 5 of those questions. And if yours is not covered because there isn't enough time, please know that you can join Mark's Facebook group and he will be covering your questions over there. And I'll be putting a link to that Facebook group in the chat as well. Having said that, have a great time. We are thrilled to have you here. Enjoy.
All right, so let's get started. So to kick this off, let me start by defining computer vision. So computer vision is basically, I like to call it the art of teaching computers, teaching robots how to see. So how to basically process a camera feed and do something useful with that. So this is a really popular topic in the development of self-driving cars. You can see in the slide I drew a Tesla. Teslas have cameras and radars to keep them on the road. So they're packed with software that basically takes this live camera feed of the road and keeps the car on the road, basically. So the software recognizes the roads, recognizes the lane boundaries, it recognizes other cars on the roads or pedestrians or cyclists, and then the software drives around these obstructions and keeps the car on the road. So that's a very popular application of computer vision. Another application would be in robotics, where you have an autonomous robot with cameras. So a robot that can basically walk around and turn its head and look at specific objects or look at people. And there, it's useful to do video processing to recognize faces. So you can see in the slide, this is a still image from one of my other applications that does facial recognition and then recognizes certain points on my face, certain landmark points, and uses those points for gaze detection. So in this case, the software is calculating where I am looking at, and I'm looking away from the camera. So if this were a robot, the robot would know that I'm not looking directly at the robot, I'm looking somewhere else. And the software in the robot could use that to react accordingly. So computer vision for self-driving cars and autonomous robots. So it's a super cool topic, very popular topic, and it's at the forefront of technology right now. A lot of stuff that I'm using to develop my computer vision apps is from academic research that's only 1 or 2 years old. So this is really high-tech at the forefront of technological development. So in this webinar, I'm going to use these 3 libraries: Accord.net, OpenCV, and DLib. So these libraries are they are specialized for computer vision, for detecting motion, detecting objects, or detecting and recognizing faces. Accord.NET is really nice because it is 100% C#. It's a managed library without any native code. So you can just install it as a NuGet package and use it in your code. And it's absolutely packed with computer vision methods and classes, with machine learning classes. So it's really useful to get up to a quick start. Now, the grand old library of computer vision and machine learning is OpenCV. OpenCV is a C++ library, so it's native code, but I have a C# wrapper. You can install the C# wrapper. It's actually a NuGet package. It's called OpenCV Sharp, and it basically wraps every method in OpenCV with a corresponding C# method. So you get full access to OpenCV from your C# code, which is pretty awesome. Finally, DLib. DLib is also a native code library developed in C. And I have a wrapper for DLib to expose all its functionality in C#. And DLib is very good for facial detection. DLib can detect faces, and it can detect landmarks in faces. So it can very accurately pinpoint your nose, your eyes, your mouth, and we can do all kinds of cool stuff with that. In this demo, in this webinar, I will use DLib and OpenCV. Okay, so let's take a look at the challenge. So here is what we are going to try to do. We have this selfie in the bottom right. So this is a very famous image. It's a selfie taken by Ellen Degeneres at the 2014 Oscars. So the guy in the front is Bradley Cooper, and to his left you can recognize Ellen Degeneres. So this picture is packed with celebrities. In the background you can see Brad Pitt. In the top right, that is Angelina Jolie. Above Ellen is Julia Roberts. And the guy all the way on the left, where you can only see half his face, is Jared Leto. So lots of celebrities. So what I'm going to do is we're going to pretend that I was there and that I was hanging out with my celebrity friends, just having some fun with Brad Pitt and his crew. So I'm going to take my face and overlay it over Bradley Cooper's face. So you can see that our faces are sort of similar. I sort of have the same beard as Bradley Cooper. So that's useful because that means that my image will, my face will kind of seamlessly fit into this image. And you can see I'm also facing the same direction. So Bradley Cooper is looking slightly to his right. And my photo also has that same head pose. So this is really useful when I do the face swap, because it means this software only has to do a minimum amount of warping, of deformation of my face to fit it inside the selfie. So what's required to do this face swap operation? So the first thing we need to do is we need to identify, or we need to detect facial landmark points. So these are known points, known locations on a face. They're numbered. There are 68 points in total, numbered from 0 to 67. And they all correspond with very specific locations on a face. So for example, point number 8 is the tip of the chin at the bottom. And you can see that the bridge of the nose, that's points 27 to 30. So all these points these are known locations on a face. And we can use a face detector, a facial detector, to scan an image and then give us the pixel coordinates of every single landmark point. So the input could be a frame in a video or a photo, and the output would be this list of 68 points with pixel coordinates of every single point. So let's start by doing that. So I'll switch over to my coding environment. So this is Visual Studio 2007. Let me just show you that. So it's Visual Studio 2017 with C# obviously installed. And I got C++ and F#. I won't be using those. But this is a fairly standard installation. You can see that I don't have much other packages installed. This is basically a vanilla Visual Studio installation for C#. That's all you need. So here's the solution. The solution is very simple. It's just a Windows Forms application. So it has one big form right here, which is hosting one large picture box. So I'll use the picture box to display the image after processing. And that's basically it. There isn't much else. There is a dlib.net.native. This is the wrapper for dlib that will allow us to call into dlib from C#. There is a shape predictor library. So this is basically a data file that is used by dlib to load a pre-trained face detector. So we can simply load this data file and then immediately use the face detector without having to train it first. And I've got my images. So this would be the selfie, Ellen Degeneres selfie. And this file right here is my profile picture that I'll use to swap the face. So let's go to the code. Let me take this thing out. So the code, it starts out really simple. I load the selfie. I load my photo. I put the selfie in the picture box. And then I call this method, process image, which basically, it loads the selfie, it loads my picture, and it has to do some kind of operation to produce this new bitmap. And then I show this new bitmap in the picture box. So all the magic happens in process image. So we'll go through it one by one. We'll go through it step by step. So to start detecting these landmark points on a face is real easy. The first thing you have to do is initialize a frontal face detector. So this is a class that will detect faces in an image. And the second thing you do is you initialize a shape predictor. And that's a class that zooms in on a face and finds the landmark points. So let me just scroll down a bit and show you this line. So this is basically how you would start. The first thing you do is you take the image, the input image, the selfie, and you run it through the detect method of the frontal face detector. And that gives you, you can see it in this tooltip here, it gives you an array of rectangles. So basically the frontal face detector scans the entire image and it will detect every single face in the image. And every face gets bounded by a rectangle. Now, I'm using a bit of pre-configured knowledge. I know that Bradley Cooper is the second face in the detection. The first one is Ellen, so the second face is Bradley Cooper. So what I'm doing here is I'm using the shape predictor, and I'm running it on Bradley Cooper's face. So this is just a rectangle that says Bradley Cooper's face is inside this rectangle. So I have this detect method of the shape predictor class. It takes the image as input and the rectangle, and it returns this class called a full object detection class. And this class contains the landmark points. And to get them out, there is a method. There's a method, let's see if I can find it. It's right here. The method is called getPart. And you feed it an unsigned integer from 0 to 67, and it gives you that landmark point. And it returns it as you can see it in the tooltip, as a point structure. And that's just a simple structure with an X and a Y coordinate. So this simple bit of link code will basically loop from 0 to the number of landmark points, which is 68. So this thing goes from 0 to 67. And then it calls getPart, and it creates this collection, this enumeration of OpenCV# point structures with the X and Y coordinates of every single point. So let me just uncomment these two lines. So what we're going to do is we're going to draw these landmark points on the selfie and then immediately return. So in this configuration, the only thing this code does is run the two detectors and then draw every single landmark point on the selfie and immediately return. So let me run that. And there you go. So here, you have Bradley Cooper, and you can see that his face is covered in these green rectangles. So these are the landmark points on his face. I could do this for every single face in the image. So I could project my face onto anyone, but I'll stick with Bradley Cooper. So you can see it's real easy to create software that can detect faces in an image and then detect these landmark points. So the software knows exactly where your mouth is, where your nose is, where your eyes are. I mean, it could basically take the shape of your mouth and detect emotions. You could say, hey, you're smiling, or hey, you look sad, your eyes are closed, you're facing away from the camera. All these things are possible just by interpreting the location of these landmark points. Okay, so let's continue. So now we've got the landmark points on the face, so we can move on. So the next thing we need to do is we need to get the convex hull. The convex hull is just the outer edge of the face. So I've drawn that here in the slides. It's just a line going through all the outmost landmark points to create a kind of contour line that borders the entire face. It's called a convex hull because the line is only allowed to curve inward. So it has to be a closed line that only curves inward, that encompasses the entire face. So you could easily generate this convex hull by hand, by taking only the landmark points that form the outer edge of the face. But you don't have to do it by hand because OpenCV has a very nice method built in that can calculate the convex hull for you. So let's do that. So I'll go back to the code. Let me stop this. So I'll re-comment out these two lines so that we can continue in the code. So now we go down. So this is the convex hull. So CV2 is a class in the OpenCV Sharp package, which exposes OpenCV to C#. And the function I'm calling is called convex hull indices. Now what this does, you can see I'm passing it the list of landmark points. So I'm feeding it a list of landmark points. And what it returns is an array of integers. So this is an array of indexes into landmark points. So it's basically giving me this array with landmark point numbers. So that will be, it will go from 0 to 7, and then 8, 9, 10, all the way up to 16, 17, and then it might jump to 22, 23, 24, and then it might jump to 29, 30. So it's only returning the landmark point indices that form this convex hull that borders the face. So now I need to turn that back into a point list. So I do that with this simple link query. So I'm just looping through every index in the hull array, and then this select just, I'm taking the landmark points and I'm feeding it the index number. So this link query will simply reconstruct a numeration of landmark points, but then only the landmark points in the convex hull. So let's draw that thing. So I'm uncommenting these lines. I'm using a little utility class to draw the landmarks. So you can see I'm drawing the landmarks in the convex hull. And then I'm calling this function called draw hull. And this will draw a little line through the landmark points. So I will still have my landmark points in bright green, but then you'll also have a line that shows the convex hull that borders the face. So let me run that. And here's the result. So again, you're looking at Bradley Cooper. You can see the landmark points are still there in green, but there are a lot less of them. You can see that the left jawline and the right jawline, those are pretty much complete. Those are all the landmark points that are detected. But then in the eyebrows, there are only 2 points. So the innermost 2 landmark points on the left and right eyebrow are gone because they would make the contour line, the convex line, curve inward, which is not allowed. So, sorry, it would make the line curve outwards, and that's not allowed. So they are removed. And everything inside the face contour is also gone. So the landmark points on the nose and on the mouth are also gone. So we only use these points. Now, the reason that we only use the convex hull is because when we warp my face onto Bradley Cooper, we don't want to distort the image too much. we want my face to exactly match the contours of Bradley Cooper's face, so that it's a clean fit. But we don't want the software to, for example, take my nose and stretch it, deform it to match Bradley Cooper's nose, or take my eyes and deform them so that they exactly match Bradley Cooper's eyes. And the reason we don't want that is because people's faces are very different. Bradley's eyes and nose are very different from mine. And if the software would try to stretch and distort my face so that it exactly fits Bradley's autonomy, we would get this really weird face that's halfway between mine and Bradley's. And it would look unnatural. And in fact, I'll show you what it looks like. At the end, I'll enable some code that will do the face swap with every single landmark point. And you'll see that we get this really strange image. But for now, to get a good fit, we only use the convex hull points. So we have them. Let's move on to the next step. So the next step is called DELAUNAY triangulation. I've drawn it here on this slide. So DELAUNAY triangulation is basically that we create a mesh of triangles that use the landmark points as their corner points, and they completely fill the face. So it's a web of triangles that completely covers the face. And the reason that we do this is because we need to warp my face onto Bradley Cooper's face. This is a non-linear transformation, a non-linear deformation, and it's really slow. Computers need lots and lots of time to process non-linear transformations. And if you want to do face swap in live video, that's kind of an impediment. So there's an optimization that you can do where you only transform landmark points. So basically you would move the landmark points on my face so that they exactly match Bradley Cooper's face. And then you can use a linear transform to move all the pixels from my face to Bradley's face. So it's basically an optimization trick where you only use a non-linear slow transform to move the landmark points. And then everything inside a triangle can be moved with a fast linear transform. So it's a mathematical trick to speed up this face warping. So let's go back to the code and add the snippet of code that will do the DELAUNAY triangulation. Let me stop this. I will re-comment this code. Okay, now before we do DELAUNAY triangulation, we have to do all the steps we've done so far on my face. So what you've seen so far was on the selfie. We have to do everything on my face as well. Okay, so let me just pause the DELAUNAY triangulation and show you the results of doing landmark and convex hull detection on my own face. So this code is the exact same code you've already seen, but now the input image is me and not the selfie. So let me run this. There you go. So this is me with the landmark points on my face. You can see the same configuration of points and the convex hull bounding my face. So you can see how cool this DLib library is. There's no configuration. I don't have to configure anything about the facial detector. This is all out-of-the-box functionality. I can just feed it any image I like, and it will zoom in on a face in the image, and then it will find the landmark points and process them. And it's all fully automated. It's very, very accurate, and it works like a charm. So the DLib library is really quite cool. But let's continue. So now you've seen that I have landmark points for the selfie and for my own face. So the next step is to calculate these DELAUNAY triangles. So the triangulation is done in this method. Now, I have to admit, I wrote this method myself. You input the hull points, and it outputs an array of triangle structures. But I can show you the method. The only reason I wrote it is because it's quite a lot of code to process the results of triangulation, and I wanted to hide that from the main from the form. So triangulation is done by this class here. So this is an OpenCV class. It's called subdiv2d, and it performs triangulation. And the triangulation is here. So this method, get triangle list, will perform triangulation on any kind of input. And to feed it input, you would basically use the insert method right here. So you initialize a subdiv 2D class, you call insert to feed it a point, and then you call get triangle list, and it will perform DELAUNAY triangulation on that list of points. Now, this link query is, I won't go into that just now. This is a query to package the results of the triangulation and return an enumeration of triangles. So I've also created this struct myself. And this triangle struct is really nice to just group 3 points together and say, this is a triangle. So let's go back to the main form. I'm performing DELAUNAY triangulation. Whoops, it's here. I'm performing DELAUNAY triangulation. I have this enumeration of triangle structs. And now I can use a little helper function called draw triangles to draw these triangles on the face. So I'm using the selfie again. So now I'm going to draw the triangles on Bradley Cooper's face. So let's run this code. So here's the result. So this is computer-generated triangulation, and you can compare it with my slide here. You can see it's the same operation. So this is a fully automatic process. You feed it the landmark points on the convex hull, and it will generate these DELAUNAY triangles that we will use to implement the face swap operation. Now, this is all the prep work you need to do the face swap. The next steps are to actually swap my face onto Bradley Cooper. So let's do that. Let me go back to the slides. And here is the actual swap functionality. So to perform face swap, all you need to do is you need to calculate the landmark points. We got those. You need to perform DELAUNAY triangulation. We just did that. And then what you need to do is take the triangles on the source image, so the triangles on my face, and warp them onto the destination face, so onto Bradley Cooper, using a transform called affine warp. Now, affine warp is built into OpenCV, so you don't have to write that code yourself. You can just call the OpenCV function to do it for you. And we have all the information to perform this warp. So the landmark points, I know the landmark points on my face and on Bradley Cooper. So I can take this triangle, and I know that the triangle is composed of landmark points 3, 14, and 24. So I can locate these points on Bradley's face, and I can locate them on my face. And then I can use this affine warp method in OpenCV to take this triangle of pixels, so basically a triangular region in my image, and warp it onto the selfie by providing these 3 new coordinates. So basically, I'm just taking a triangle and rotating and translating it onto a new image. It's a very simple translation. So the movement of the landmark points from my face to Bradley's face will be nonlinear, because, I mean, I have no idea how our faces are angled, our anatomy is different, Bradley's skull is different from mine, so all his landmark points will be in slightly different locations. So that's a nonlinear transformation. But that doesn't matter, because I know the coordinates, I know exactly where his landmark points are, and all the pixels inside the triangle can be moved with a simple linear transformation. So there's no rocket science behind that. It's a very simple geometric transform to transform the triangle from one image to another. And it's all built into OpenCV. So let's see what that looks like in code. So I'll comment out these lines again as we go down a bit. So here is the first method to perform the triangulation. To perform the transformation. So what this method does is it takes as an input the landmark points on my face and the landmark points on Bradley's face and the triangles, and it creates an enumeration of warps. So these warps, I've created the structure myself, the warp structure. But again, it's really simple. Let me show it to you. It's up here. So here we go. So a warp is nothing more than a source triangle and a destination triangle, and that's it. So two triangles, one on my face and one on Bradley's face. So this it's a simple data structure to contain the information that I will need later to actually perform the warps. So this method, getWarps, will take this input data and create an enumeration of warps, and then I will feed that information into this method, applyWarps. So applyWarps takes my face, my image, it takes the dimensions of the selfie, and it takes this enumeration of warps, and it produces a new image, which contains my face, rotated, and translated, and resized to exactly match Bradley Cooper's face. So let me uncomment this line. So I'm just going to uncomment this line that immediately outputs this warped image so that you can see what the output is of this translation. And here it is. So now you're looking at the selfie, but everything is in black except my face. And my face has been rotated, translated, resized to exactly match the convex hull of Bradley Cooper's face. So we're almost there. The only thing we need to do now is to alpha blend this image into the selfie. We have to basically erase Bradley Cooper, erase everything in the selfie which is under my face, and then blend my face into that image. So let's do that in code. It's a fairly simple operation. Yeah, I'm doing it right here. So the code to perform the blending, to do the blending, the first thing we need to do is we need a mask. We need an image which is all black, except for the pixels in white that we need to erase from the selfie. So to do that, there's a very handy function in OpenCV called fill convex poly, which takes a contour line, it takes like a hull contour, and it fills it with pixels. So in this case, I'm taking the Bradley hull points, so this is the outer contour of Bradley's face, and I'm basically drawing a line around Bradley's face and then filling the entire area in white. Yeah, this is the color. So I have this mask, which is now my face in white and everything else in black. And then to perform the blending, all I need to do is erase Bradley Cooper from the selfie. And you do that with this line. So this is a multiply method in OpenCV. It multiplies one image with another. So multiply is really, really nice if you're doing masking, because if you multiply a pixel by 0, it turns black. And if you multiply a pixel with white, it retains its color. So you can use a mask combined with the multiply method to basically erase anything out of an image. So this line will erase Bradley Cooper's face from the selfie. And then I can simply add the pixels in my image to the selfie. So where Bradley's face used to be, there's just this black hole now, and I can fill that black area with the pixels from my image. So these two operations will do the blend, and then here I return the result. So let's do that. Let me run the code, and you can see what's happening. So here is the face swap. We're almost there. It looks pretty cool. You can see that my face has been rotated and resized and sheared to exactly match the convex hull of Bradley Cooper's face. But there's one problem, and that is our skin tones don't match. The lighting at the Oscars is, of course, different from the lighting where my profile picture was taken. And we have different skin tones, so you will always get this weird line just above the eyebrows where the skin doesn't match, and you can clearly see that it's just one image blended on top of another image. So the final step, what we need to do, is adjust the skin tone. So we need to take my face and recolor all the pixels in my face so that they correspond with the average skin tone of Bradley Cooper's face. Now that sounds like a really complicated operation, but it's actually really simple. You can do it with a single method in OpenCV. There's a method in OpenCV called seamless clone, and that method does all the work for you. It will look at the image that you're blending into. It will look at the average color around the area where you're doing the insert, where you're doing the blend, and then it will recolor the pixels in the other image so that they match. So it's basically a black box operation that does all the work for you. So let me show you what that looks like in code. I will comment out these lines again so that we can continue with the code. Here we go. So here's the seamless clone method as part of OpenCV. It needs a bit of input data. It needs the image that we want to blend. So this is the image which is all black with just my face. It needs the selfie, so the image that we're blending into. It needs a mask. So this is an all black image with my face in white. So it uses the mask to basically erase Bradley and then replace it with my face. But it also needs this. This is a point, and this is the center where we are inserting into, basically the center of my face. The method needs this central location because it's going to look for the average color around this location and use that color to recolor all the pixels in my face. So this little bit of code here calculates the center point of Bradley Cooper's face because that is the point where we are inserting into. And finding a center point, again, is really easy. There's this handy method in OpenCV called bounding rect, which will find the bounding rectangle that encompasses all of these points. So I feed it the whole points and I get this rectangle. And then I can just use this simple math to find the center of the rectangle. So that gets me the center where we are inserting the face. And then this method will perform a seamless clone. It will blend my image into the selfie, and it will output the results into this new image. So right here, I'm using some OpenCV magic to create an empty image with the same size and type as the selfie. And then the seamless clone method can blend into that new image. And finally, we return that blended image. So let me run this. This is the full code of the face swap. And here's the result. So now you can see that you can kind of still see that there are hints. You can see that my face, the skin tone of my profile picture here below my mouth is still sort of visible. So you can see that it's a darker shade. But then up here we have, this bit is Bradley Cooper's forehead. And you can see that my skin naturally changes tone as we go up in my face. So the seamless clone method has recolored the pixels in my face to match the average skin color of Bradley Cooper. So basically, what the method does is it makes sure that at the edges of the image that you're inserting, so at the edge of my face, it recolors all the pixels to create a seamless match. So at the top, my skin is recolored to match Bradley Cooper's skin, and at the bottom, my beard is actually made a bit darker so that it matches Bradley Cooper's beard color. Because I have blonde hair and Bradley has black hair. So the seamless clone method has to make my hair a bit darker to create a good match. And here's the final image. So you can see it's pretty good. Because I was facing in the same direction as Bradley, there is just a minimum amount of deformation in my face. So it looks pretty natural. Also, I have kind of the same beard as Bradley. So the entire image kind of looks the same. And the seamless clone method has recolored the pixels to create a nice seamless match. So now let me get back to a thing that I covered on earlier. This is face swap. performed with only the convex hull that borders my face. What would happen if we do the face swap with all landmark points? So we include the nose and the mouth and everything. So let me do that. So I'll go back up to where the DELAUNAY triangulation is performed, which is here. So here is the DELAUNAY triangulation, and here is where I calculate the warps that describe how to warp my face through Bradley Cooper's. And you can see that the DELAUNAY triangulation method receives the hull points, Bradley's hull points, and the warp function receives my hull and Bradley's hull. But what I can also do is just call those methods again, right here, with every landmark point in Bradley's face and every landmark point in my face. So now I'm basically doing triangulation again with every single landmark point. So let's run that. Here's the result. So this is not a good warp. So why did this happen? First of all, a huge difference between my face and Bradley Cooper's face. Let me just go back to the source images right here. So a huge image is Bradley Cooper is smiling. He has his mouth open. And in my profile picture, my mouth is closed. Now, the face swap algorithm is going to try and deform my face to match Bradley Cooper's mouth. And because there are no teeth visible in my image, you get this weird effect where my lips are basically just stretched. So the face swap algorithm, yeah, it's trying to show my teeth, but it doesn't have an image of my teeth. So you get this. And if you look at my eyes, you can see that my eyes are really, yeah, they're deformed in a really strange way. Basically because the shape of my eyes is different from Bradley Cooper's. So what the algorithm has done now is it has tried to deform, to warp my eyes to exactly match the contour of Bradley Cooper's eyes. And because we have a different facial anatomy, it looks really weird. So this is the reason why you always do face swap with hull points and not with every single landmark point, because the differences between faces are quite large, and you get these weird effects. So let me fix the code. I'll uncomment these extra lines that were that I inserted earlier. So now again, I do the entire algorithm. I run the algorithm just with the hull points. And there's the result again. So this is the face swap done right. Now, I have run this image through an Instagram filter to clean up my skin tone even more. And then you get a really nice result. The Instagram filter kind of blurred my skin tone a bit more and made it match the overall skin tone of everybody else in the picture. So you can really do cool stuff with face swap and insert yourself into any kind of celebrity situation. Let me show you one more thing. I've showed you these two methods, get DELAUNAY triangles and get warps and apply warps, but you haven't seen the insides of these methods. So I'm going to show you the apply warp method, which is here in the utility class. So I wrote that myself. So here is apply warp, and I'm looking for a specific, here we go. So this method, this is the affine transform method in OpenCV. So this method will get a transform. It returns a matrix, basically, that describes how to transform triangle 1 into triangle 2. And then once you have that matrix, you can call this method called warp affine, also in the OpenCV library, which will actually perform that transformation. So I feed it a source image and a destination image, and I feed it the transformation that I just calculated up here. It also needs the size of the destination image, and it will basically take the triangle in image 1 and transform it into image 2. So this affine transform operation to transform triangles from a source face to a destination face It's all built into OpenCV. So it's these two methods, get affine transform and warp affine, that do all the heavy lifting for you. So all this code that you see that I wrote myself is just code to process coordinates, translate coordinates from OpenCV to DLib and back again, resize images so that the algorithm runs faster. It's basically all maintenance code. But the actual magic, all the heavy lifting, happens inside these two OpenCV methods. So OpenCV is a pretty powerful library, and if you combine it with DLib, then you can do some awesome stuff. You can calculate the landmark points with DLib, and then you process them with those built-in OpenCV functions to do all kinds of cool stuff with faces. So let's move forward again. So we did the skin tone adjustment, and that's the final step. So this is how you swap faces in C# code. And here's the final result. So this is the image I mentioned earlier. This is the Instagram image that I created. So basically, I just took the image, I ran it through Instagram, I applied a filter, I can't remember which one, but I applied a filter that kind of made everybody's skin a bit lighter. And the effect was that in my face, my skin tone became more uniform. So this is a pretty cool match. You can see my left jawline, there's a slight dark contour. I'm not sure if you can see my mouse, but here on the left side of my face, there's a tiny dark contour that still shows a hint that this is a face swap operation. But this is a pretty awesome result. So face swap is part of a computer vision bootcamp that I created. So this entire exercise is one of the tasks in the bootcamp. It's a 3-week bootcamp, 15 days, where every day there is a new task, a new computer vision task to perform. And everybody in the bootcamp will write all of this code themselves in only 2 to 3 hours. So I've shown you a lot of code, but you can actually write the entire thing yourself in 3 hours, given enough information from the start. So in the bootcamp, I'm going to take a group of students through these computer vision tasks, and they will create 10 different real-life applications around computer vision and learn all about cool stuff like shape detection, motion detection, well, face detection, like I've shown you in this webinar, but also pose estimation and gaze estimation, like which direction is your head turned, where are your eyes looking? Are your eyes looking straight ahead or up or down? We're going to read emotions of faces. So it's packed with cool stuff. So it's, if you want some more information, there's a URL at the bottom. So the bootcamp is called Computer Vision in C#, Computer Vision in C#. And you can find it on the Mensch website, mensch.co. So mensch.co/computer vision in C#. So I'll give you a bit more information about that bootcamp. It's an online bootcamp, which means that it's basically, it's like a course where you would go into a training location and receive hands-on support, but it is entirely online. So if you compare that with different formats of learning that you have nowadays, if you look at affordable education, Udemy is like the star, the king of affordable education. It's like courses are $10. So you can easily buy a course, you get like 3 to 8 hours of content, and you can learn new stuff for almost no money. Unfortunately, Udemy is extremely passive. You buy the course, you watch the video, and that's it. You're not actually using the knowledge. You're not coding while you're learning. And we instructors, we can see that in the completion rates. A typical Udemy course has a 10% completion rate. So out of 100 people that buy a course, only 10 people will actually reach the end of the course. So that's super low. So if you look at other alternatives, you could go to Harvard, to an actual university, and get an education there. Unfortunately, that's super expensive. And if you think about it, it's still passive. You're listening to professors sharing their knowledge with you, and then you learn the stuff, and then there's an exam where you have to demonstrate that you've learned it. I studied physics in Holland, so I have a degree in physics. And my whole education was like that. I was in auditoriums, professor explaining stuff to me. I had to memorize it, and then there was an exam, and I had to demonstrate that I had learned that knowledge. So I wasn't actually doing anything. I wasn't building rockets or super colliders with the knowledge that I learned. So that's kind of a shame. So if you look at active education, there are boot camps, like Dev Bootcamp, which are super hands-on. Like you go to a training location, and for 12 weeks, 5 days a week, you learn how to code, learning by doing, and you have instructors at a moment's notice who can come up to your desk and help you. You work together with your colleagues to create projects. So it's this super hands-on way of learning. Unfortunately, it's also expensive. A typical bootcamp is between $10,000 and $50,000, so that's a lot. I actually gave bootcamps as an instructor in the past. So I was at the front of the class teaching people in a bootcamp, and I remember the fee was about $1,000 per student per day. So that's pretty expensive. So this is an online bootcamp, so it's an entirely new concept. It's similar to a traditional bootcamp, but all the interaction with the instructor, with me, is online. So I'm basically supporting you through Skype, through Slack, through Zoom, through Facebook Messenger, through email, all online channels. So it's a lot cheaper than a traditional on-site bootcamp because we don't need a training location, and I don't need to be on-site for 8 hours a day. Neither do you. So it's a really convenient way for you to learn knowledge, hands-on, learning by doing, from the comfort of your own home, and still receive all the support that you would have in a traditional bootcamp. So this is how that would work. It's a 15-day bootcamp. Every day I give an assignment. The assignment takes about 2 to 3 hours to complete. And then you get to work. I give you a couple of hints, the minimum amount of information that you need to know to get started. And then you get to work, and you work on the assignment. And while you're working, I support you through Facebook messengers, through group calls. There's a 1-hour group call every day, and through one-on-one sessions. So these are Skype sessions where I can call you directly, you can call me, and we have one-on-one support to help you with a specific concept. And at the end of the day, you submit your results, and I give feedback. So it's learning by doing, hands-on bootcamp, and all the interaction is online. So that's super cool. So here's a list of all the applications that you would build in the bootcamp. So if you look at number 8, an app that inserts your face in a selfie, that's the app that we have, that I've covered in the webinar. So you would be building that exact same app yourself. But there's also a lot of other cool stuff. Number 2, a highway lane finder. So a self-driving car filming a road, and you have to identify the lane boundaries of the road so the car stays in lane. I've got a video of someone doing a speed run of the Super Mario game, the first level of Super Mario, and your assignment will be to build software that tracks Mario. So you have to draw a little targeting rectangle over Mario and keep tracking him throughout the entire game. It's a lot more complicated than you think. There's a video filter, number 5. You create a video filter that draws a little mustache on your face, just like Snapchat or Instagram. We're going to build something, we're going to build a camera. I don't know if you've had this, but someone takes a picture, you're at a social gathering, somebody takes your picture, and your eyes are closed in the picture. And then, you know, everybody looks cool except you because your eyes are closed. So we're going to build a camera that refuses to take bad pictures because it looks at your eyes, and when they are closed, it simply refuses to take the picture. Again, it's easy to do when we have landmark points. We're going to build an app, a Netflix app, that pauses video when you look away. So you can be in the couch, in your living room, watching your favorite Netflix show, and then when you get interrupted and you look away, the app helpfully pauses the show so that you can finish whatever you are doing, and then when you look back at the TV, the app continues playing. With head pose detection, we can build apps like that. You are going to build that app in the bootcamp. So these are 10 pretty awesome apps, if I say so myself. And during the 15 days of the bootcamp, you would be building these apps all by yourself. So here's what's included in the bootcamp. It's 15 days of hands-on support. It's a group call, 1-hour group call on Zoom every day. In fact, it's this very Zoom session that we are in right now. We'll use this Zoom session for the bootcamp, for the group calls. There are 2 private 30-minute Skype calls with me, where you can discuss anything you like. If you're stuck, or if you want to talk about your career or computer vision in general, I'll support you in these 2 calls. And there's continuous support in Messenger. So throughout the entire day, I will be available on Messenger. So through Facebook Messenger, you can contact me anytime with any kind of problem that you have. And there's Facebook community access. I'll create a Facebook group around the bootcamp and enroll you into the group. And then we can discuss the apps and computer vision challenges in that group. Plus, you get access to all my source code. So I've done all the exercises in the bootcamp myself. I have all the code. I'll share everything with you. And I'll give you the C# wrappers of the DLib and OpenFace library. Now, we haven't talked about OpenFace yet, but it's basically DLib on steroids. It's 1 year old. It's super up to date. And it's this amazing facial detection library that uses convolutional neural networks to identify faces. It's a pretty revolutionary library. It has a recognition score that's slightly higher than a human. So this library is better at recognizing faces than an actual person is. And we're going to use it in the bootcamp. So that's the end of my sales pitch. So I invite you all to go to this URL, mensch.co/computervision in C# and check out the bootcamp. The bootcamp is a live event. It runs from February 5th to February 21st. And it means that you have until Sunday to enroll, and there are 20 seats in total. So don't wait too long don't wait too long to enroll, because right now there are only 10 seats left, and on Sunday I have to close the enrollment. So if you're interested, check out the website, go to mensch.co Computer Vision in C#, take a look at the bootcamp, and if you like it, enroll. And if you like it, don't wait too long, because all seats might be gone in a few days. Okay, so that concludes the webinar. So if you want to reach me, here's some general contact information. So I'm on social media. The second Facebook link that you see, that's the C# Performance Architects. There's a typo in there, I'm sorry. It's C# Performance Architects. So I invite you to join that group. It's a Facebook group all about C# performance optimization. So we talk about how to write C# code that runs as fast as possible, which is, again, really cool. Okay, so now let me give the word back to Sansolis.
So, wow, Mark. Yes, those apps are really amazing. It's not just you who says that. And it has been amazing also to hear you teach. I have indeed some questions. I have here, for instance, from Roger, who asks, what if one of the people is wearing glasses? Can the software deal with that?
Wow, awesome question. Fantastic. Yeah, the software can deal with that. Well, it depends on the glasses, basically. The software uses contrast in the image to detect eyes. So eyes tend to be a bit light. Eyes have white around them. They have a round pupil and a bit of white around them. And then there's usually a shadow above the eyes because our brows cast a shadow downwards. And the face detectors are trained to recognize these contrasts, these contours, and identify them as eyes. So if you wear glasses which are like transparent, like normal prescription glasses, and there is no reflection on the glasses so that the camera can look through them, then it will have no trouble recognizing the glasses. Unfortunately, if they are sunglasses, then there's nothing to latch onto. The software will not be able to identify landmark points on your eyes. However, DLib is powerful enough that it can estimate where your eyes would be. So what DLib would do, it would correctly detect your nose, the contour of your jaw and your mouth. It wouldn't be able to detect your eyes because there are sunglasses, and then it would simply project the eye points into the sunglasses based on averages. It would say, okay, if I know that the nose is here, then the eyes, the left eye would be, you know, slightly to the left of the nose, and the right eye would be slightly to the right of the nose. So it will do a best estimate to put in these points. So that's pretty powerful stuff. DLIP is, it uses that for every single landmark point. So you can even tilt your head 90 degrees away from the camera, and it will still recognize every single landmark point. It will simply guess the points that are not visible. And open face is even better. Open face, you can turn 180 degrees. So you can turn all the way around and face away from the camera, and open face will simply estimate everything, your nose, your mouth, your eyes, and say, okay, you know, it can see the contour of your head, so it will say, okay, I guess the mouth is here. So it's powerful stuff. One final thing, if you want, you can create a detector that is trained on glasses. So these detectors have out-of-the-box training files that allow them to detect eyes and nose and mouths, etc. But you can build your own and train it to detect glasses. And then it would identify glasses in every single face.
Okay, so there is one more question from Roger. He says, can this software use a feed from a webcam to scan a person's face and compare it to a file photo to, say, replace a user ID and password?
Yep, absolutely. So we didn't cover that in this webinar, but what you would do is you would take a camera feed and then extract every single frame. And then you would create a, you would perform, it's called hog detection, H-O-G, hog detection, histogram of gradients. And it's a mathematical trick to turn a face into a vector of 128 numbers. And this vector describes the features of a face in high detail. So hog detection is fantastic to basically just turn a face into a list of numbers. And then what you would do is you would use machine learning, and you would train a machine learning algorithm to recognize faces. And for that, a very popular choice is something called a support vector machine, an SVM. A support vector machine is a binary classifier, so it makes yes-no decisions. So what you can do is feed this hog description of a face into a support vector machine and have it answer one single question. Is this user ID 1? So you have one support vector machine, and the only thing it does is identify user 1. And it answers yes or no. It says, yes, I have 80% confidence that this is user 1, or it says, no, I have 70% confidence that this is someone else. So for every person in your organization, you would have a separate support vector machine that identifies that person. And then you would take the camera feed and you would input the camera feed into all support vector machines simultaneously. And then you will get this list of probabilities. Every support vector machine would say, well, this kind of looks like Pete, 40%, or it could be Charles, 80% confident. So you take all these numbers and you basically take the highest scoring output, and you would say, is this person? And this is how commercial facial detectors are built. They, most of them use histogram of gradients to convert a face into numbers, and then a support vector machine to match that list of numbers to a particular user.
Okay, so it's about 5 minutes over the hour. We have one more question, and we have said that we would answer 5 of them. So if anyone wants to add any other questions, please do so right now. I am going to read now a question from someone called SH, and he says, hi, so for a face of, let's say, 68 points, something is also defined for the entire head, and when it is not already defined, let's say for an object, there is what is needed in library probably, but what could be a general rule? As in, how do we know we have enough or not enough points defined and where to put them? Thank you.
Okay, so let me see if I understand this question correctly. So DLIP returns 68 points. And the reason is that the DLIP face detector was trained with faces with 68 points marked on them. So it's just a convention. You can train your own facial detector with as many points as you like. And in fact, there are face detectors that have grids of 120 or 130 points, lots more points than the ones used in DLIP. So 68 is not a hard limit. You can have as many as you want. You can define the points anywhere you like. So if you want to have like the hairline of people, at the top of the forehead, you could train a face detector with those extra points, and then it would recognize those. And in fact, there are some commercial face detectors that detect like a couple of 100 points on a face, so that they capture the entire facial geometry, the entire 3D surface of your face. Now, if you're wondering where these points come from, they have been manually marked on test data. So there is test data, like hundreds and hundreds of photos of people, and in every photo, the landmark points have been marked by hand, by a person. And these test files are online, so you can download them, and you can use them to train your own facial detector. And you can draw as many points as you like onto these test images to train your detector to detect these extra points. So I've been using DLIP. The data file that I had to load into DLIP before I could start, that's basically the training results. So the results of the training session on all these test images for 68 points. And DLIP can actually handle larger sets of points as well, just by loading different data files. I think there is 132 set of points for DLIP that you can just load. So you can grab the data file online and load it into your detector. I have to check that though, but I kind of remember that I saw a 132 file somewhere as well. So to answer your question, if you need more points, train your own detector to recognize more points than the standard 68. And where the points are coming from, they have all been hand-marked into test images by a person. So basically, this is assisted learning for software. We show the computer what the result is like, and then we train the computer to match those same results. That's how all these facial detectors are programmed.
Okay, so yeah, as I says, I see the idea. Great answer. Thanks again.
Awesome, thank you.
And we have two more questions. One from M. Carter, who says, Mark, with C# and the libraries you have demonstrated, what's the chance it is fast enough to do face swapping in a video feed with two people in the frame in real time?
You can do it. So you can do face swapping in real time with two people, but you would have to do a few optimizations to get an acceptable frame rate. I'll let you in on a secret. This whole operation, this whole face detection and landmark detection, seems like a really complex operation, but oddly enough, the slowest operation is the facial detection, so finding the rectangles in the image where the face is. The fastest operation is the shape predictor, so the operation that gets these 68 landmark points. Now, you're not going to believe this, but the method to extract these landmark points takes 1 millisecond to run, just a single millisecond. So landmark detection can easily run in live video for every single frame. So to speed up the slower operations, like the face detection, what we would do is we would only perform the face detection every few frames. So like for the first frame, I do face detection, that gets me the rectangle. Then I do landmark detection, that gets me the 68 points. And then for the next 10 frames, I assume that the rectangle doesn't move. So I take that same rectangle from the first frame, and I detect the landmark points inside there again. And then on frame number 11, I restart the face detection, and I calculate the new rectangle, and then calculate the landmark points inside there. So for every frame, I calculate landmark points, and for every 10 frames, I calculate where the face is. That gets me real-time performance, but it also means that if I move very quickly in the video, the software won't be able to keep up with my movement. So basically, you would have fluent face swap in live video with two faces, but then when one person starts swaying their head from side to side quickly, the face would lag. The face wouldn't be able to keep up with the head, and it would kind of follow the head. And then when you stop moving, the face would catch up and snap back into place again. So if you're okay with that behavior, then you could easily do it on live video. By the way, one more thing. You can use motion detection to track the head in a way that's faster than face detection. There's an algorithm called cam shift. So I invite you to look into cam shift. What you can do is detect the face once with the frontal face detector and DLIP, and then use cam shift to track motion for the next 10 frames. And then frame number 11, you call the frontal face detector again. And then for the next 10 frames, you use cam shift to detect motion. If you do that, then you will be able to track fast head movements in real time.
Okay, and we have a fifth question from Chris Anders, who says, what are the average requirements for processing a 720p image at 30 FPS? Can this be used for distance calculations using known focal lengths and distances from lens to lens on dual cameras?
Absolutely, absolutely, yeah. If you know the specs of your camera, then you can provide a camera transformation matrix into the OpenCV methods to adjust for, well, basically for the geometry of your camera, and then you can use that for distance calculation, absolutely. In terms of performance, you can run at 30 FPS. The code I've been using has a 640 by 320 video window, so it's not 720p, it's lower. And in my code, with a few simple optimizations, I was able to get a 30 FPS frame rate. So you can definitely do it, but you're going to have to do some tricks. So you can't do the processing on every frame. You would have to do it every third or fourth frame. And you would have to be very careful that that your code runs as fast as possible. So, I mean, having a GPU obviously helps. My code actually runs in parallels in a virtual machine. So I'm running this on a MacBook Pro that hosts Parallels, that hosts Windows 10, that hosts Visual Studio. So it's kind of the worst possible setup for computer vision. And still, I'm able to get close to 30 FPS. So if you have a Windows machine, where Windows 10 is running on bare metal directly, you should be able to get 30 FPS with 720p. I think it's possible. I haven't done it myself, but I'm optimistic that you would achieve that.
Okay, so Chris Anders says, I will use CUDA. Thank you so much for the tips. And we have also a message from M. Carter who says, thank you, Mark and Sonsoles. Looking forward to next Monday. So I guess this is one of your students in the bootcamp already.
So only 9 seats left, guys. So be quick.
Okay, and he has some more questions. Michael, you can either post those in the Facebook group or on Monday with Mark.
Exactly.
So thank you, everyone. I hope you all had a great time, and see you next time at the next webinar.
Yeah, thanks everyone. See you at the next webinar, and I hope to see you in the bootcamp on Monday.